Good morning. I welcome you all to the series of lectures on thermodynamics. Today we are going to discuss about the flow work and work in stretching a wire. First, let us look into flow work. See, this is the control volume through which differential mass of fluid is entering and leaving. At this area, at this location, the pressure is P1. At this location, the pressure is P2. Okay, corresponding volume and V1, V2, temperatures T1 and T2. It is this flow work is only accounted in the case of open system where mass crossing the boundary. Flow work means because of the flow of the fluid, the work is coming. So that means this flow work means flow of fluid takes place means it is only the open system. So that's why it is accounted in the case of only in open system where mass crossing the boundary. Okay, let a differential volume, this open system can also called as control volume. Let a differential volume dV enters the control volume against the pressure P as shown in the system. See, as shown in the figure, we have shown differential volume of fluid is entering the control volume against the pressure P. Now flow work W delta W is equal, already you know some value, some equation PdV. Flow work is equal to delta W is equal to PdV. Total work means W is equal to integral 1 to 2 PdV, we write that one. Okay, that's what we use here also. Flow work delta W is equal to PdV. But dV is equal to, this is volume, is equal to V into dm. V is the specific volume in meter cube per kg. Dm is the mass, differential mass. So kg get cancelled, meter cube. So dV can be written as V into dm. Then delta W is equal to P into dV means V into dm. V is the small v, specific volume. Whereas V is equal to specific volume in meter cube per kg. dm is the differential mass entering the control volume in kg. Then work transfer per kg of flow. If this is the work transfer, but work transfer per kg of flow means delta W by delta M. Then delta W by dm is equal to, if I write by dm here, this dm cancel, PV will get. This is called flow work per kg of mass. This is flow work per kg of mass. This is total flow work. This is flow work per kg of mass. Then flow work at inlet of the system is equal to P1 V1. Flow work at outlet of the system is P2 V2. Okay, if you want in between, you can consider any other state, you can write the flow work there also. Okay, this is about the flow work. Now let us look into the work in stretching a wire. Work in stretching a wire. Here, let us consider a elastic wire. When an elastic wire is stretched through a distance dl, see, elastic wire applying the tensile force T on this wire, and we consider that as a system. Okay, initially the length of the wire is L. After applying tensile force, tensile force means after applying tensile force, the length will increase by an amount of dl. Okay, now the work done on the system, that is wire, is delta W is equal to, it is something like linear work. So force into displacement, force is the tensile force, so T, dl is the change in length. Okay, force into displacement, this is how dl is the distance through which the wire is displaced. Okay, T into dl. Minus sign becomes this work is done on the system, because negative sign indicates work is done on the system, that is wire. T is the tension in the wire, tensile force. Then Young's modulus capital E is equal to stress by strain. Stress is sigma, strain is epsilon. Then stress is equal to force by area. Already force is tensile force T, area is the cross sectional area of the wire by epsilon. Then from this I can write T is equal to, this A also come here, then T is equal to E capital E, Young's modulus E into epsilon into A. So this is equation number 2. From 1 and 2 I can write delta W is equal to, T means minus E epsilon A into dl. Then already strain is equal to change in length by original length. Change in length is the dl. After applying the force, the change in length changes by an amount of dl. By original length is L, dl by L. dl is change in length, L is the original length. Then from this I can write dl is equal to L into d epsilon. I write delta W is equal to minus EA epsilon, dl means L into d epsilon. Okay, now what happens, see, W is equal to integral 1 to 2 delta W. Delta W is a small work transfer, but I want now total work transfer. Integral 1 to 2 delta W is the minus EAL epsilon into d epsilon. Just now we have seen. Then is equal to so EAL is the constant, so L is original length, that is not that is constant, that is not changed, so you can take it out. Area is constant, the epsilon is constant, so you can take it out. Epsilon into d epsilon, integral 1 to 2 epsilon into d epsilon. Then W is equal to minus EAL into, it is something like integral x dx, then it is become x squared by 2. So here x means epsilon squared by 2, integral 1, sorry, limits between 1 and 2. If I apply the limits, W is equal to minus EAL, upper limit epsilon 2 square minus lower limit epsilon 1 square by 2. So epsilon 2 is the strain at state point 2, epsilon 1 is the strain at state point 1. So this is the work in stretching a wire. Thank you very much.